Okay, so I'm going to explain in this video the basics of neural networks in general and mathematical terms without getting into the actual pieces of code. So by the way, so if you are very familiar with the basics of the neural network, how it um, trains, you may skip this entire video and jump into the next one, explaining the specifics of the code I provided. But this is the contents. So I first overall talk about what is machine learning anyways. So the next section is about how training actually works. And this chain rule is the mathematical foundation about how it can, train, and specifically the basis of what is commonly known as the backpropagation. And the section 4 talks about for each specific layer how this backpropagation actually works. So what is machine learning anyways? So the machine learning, or more specifically, the supervised machine learning, it is given as an input a set of what is known as a training data set. So training data set is a collection of pairs. So each pair consists of xi input to the function um, you wanna obtain by training. And TI is the associated true output for this input. So you essentially given the input and output of the function you wanna obtain by training. And each xi or input is normally a real vector. So it's many real values. It may be a vector representing a word in the natural language processing, or vector representing pixels in image, image recognition or image processing type of network. So each TI, the output for this xi, is typically a real value in the case of regression, or discrete value, 0 or 1 in the case of binary classification, yes or no. Okay, so for example, this is a spam email, or this is not a spam email. Or in more general, a discrete value from, for example, 0 to 9 in the case of so-called multi-class classification. For example, in the digit recognition, it will be a value from 0 to 9. So it depends on the task. And the goal of a supervised machine learning is to find a function f that sort of matches this training data very well. That is, so the function you want to obtain is a function such that for each input xi, the output value of this function is in some way close to the true output, the given true output for this xi. So if this happens for all pairs given in the data set, it will be a good approximation of um, a function that behaves like this, right? So to put it somewhat more formally, the goal is to find f that minimizes an error or a loss, which is defined by something like this. So for each sample given in the training data set, you compute f of xi, measure the error or the difference between whatever is output by this f and the true output. and you sum the error over the entire data set, which is defined as the loss of this f with respect to the given data set. So the goal is to minimize this loss, or the find f that minimizes the loss. So like I said, this error term, error between yi and ti, is a function that in some way measures the error or the distance between the predicted output and the true output. So, but a caveat is that finding a good function from the space of literally all possible functions is neither easy nor meaningful. So it is not easy, obviously, because there are huge number of all possible functions, right? But somewhat more importantly, it is actually not very meaningful if you search the entire space of functions, because you can easily find a function that returns exactly ti for each of the given samples in the given data set. Okay, but returns meaningless or some random values for any value outside this training data set. Well, so if the search space of is literally all possible functions, you can easily build something like that in a way that just remembers whatever is given in the data set, but does nothing else outside the data set, right? So this formulation is actually not very meaningful. So we therefore normally fix a such space of functions to a fixed expression parameterized by some parameters, or normally called weights, and find a good function fw in this fixed subspace. So it is something called parametric models. So you are not searching for any function, but you are instead searching for a function in a fixed function space. Well, fixed in the sense that the expression itself is actually fixed. So you can change the function only by changing some parameters. Right, so you can think of it as just, for example, polynomials of degree 2 or up to 3, and parameters are just coefficients of the polynomials. So the task is then to find the value of w, the parameters, that minimizes the loss. So this slightly different formulation, but conceptually it's very similar to what I have just described in the last slide. So the only difference being that this part is not an arbitrary function. So it is just a set of parameters. And you fix the parameters and build a function and compute the loss. So the goal is to find the value of parameters, the weights that minimize this loss. So I will explain this in a specific example, a very simple example, something called linear regression. So in this specific simple example, training data is just a collection of a pair of real value and a pair of real values. So in other words, both inputs and outputs are a single real value. And we fix the search space to a set of polynomials of degree up to 2. Then a function, all the functions in that such space can be parameterized by three parameters. The coefficients of polynomials of degree up to 2. Or more specifically, something like this: w2x squared plus w1x plus w0 constant term. So this is fw of x. And let the error function be a simple square distance between the whatever is output by the function and the true value, specifically like this. So the task is then to find a set of parameters w, three real numbers, that minimizes the loss, which is the summation of errors over the entire data set, which is more specifically simply this. Okay, here's the very simple example, but it's still instance of the machine learning. So let me talk about a somewhat more realistic example, which is handwritten digit recognition. So in this example, training data is again a collection of input and output, but each input is a vector of pixel values of an image. And Ti, the output of each sample is the class it belongs. And in this case, as we are recognizing an image as one of the digits, the class is integer from 0 to 9. And the search space, well, of course, we can design the search space in many ways. But in this particular example, it can be written mathematically as something like this. But let me explain in the picture. So here's the input, and as the first step, it goes through something called convolution. So convolution of matrix W0 and vector X. Well, it is actually two-dimensional array, which is an image, 2D image. The output of this convolution is then taken by something called the ReLU. So you don't have to know what the ReLU is at this point, but it is a very simple function. I'll get to that later. And the output from the ReLU is then taken by another simple function called the maxPool. And it is then multiplied by another matrix. So it is essentially a matrix vector multiplication. And the output of this matrix vector multiplication is then fed to something called a softmax. Again, I'll come to the definition of a softmax layer. But so the only point here is that yeah, it is composition of many functions, and the weights we are trying to find these W0 and W1 associated with this convolution layer and the matrix vector multiplication layer, which is also known as commonly known as the free connected layer. And the output of this function or the model is which is the output of the softmax layer. So it is 10 vector, so 10 element vector, each component of which represents the probability that model thinks that input belongs to each particular class. So in this case, you have 10 classes from 0 to 9. So it is a 10 element vector. So a loss function that measures the distance between the true value and whatever is output by the model or F is something called the negative log likelihood function, commonly used in multi-class classifications. So its definition is simply as this. So this is a 10 vector. So T is the true class, so an integer from 0 to 9. So negative log likelihood is literally taking the log of the component specified by the true class and take the negative of this. So I come to why the loss function is defined as this later again. But at this point, you just note that if yt, so the component corresponding to the true class output by this function we are building is 1, then you take the log, so this loss becomes 0. So this is exactly what we like to have, right? So if the true class is t, the we like the model to output a vector whose the true component is 1 and all other components 0. So this is the goal, right? On the other hand, if the model says, okay, the component corresponding to the uh, true class is very small value, let's say the 0.1, then if you take the log, it's going to be negative value. So if you take the negative of the negative value, it becomes a positive value, right? So it is the loss, right? So you just know that why it at least makes sense to define the loss function this way. But you still wonder why you have to take the log here. So I'll come to that later. But anyway, the task then is to find um, those weights W0 and W1 that minimize the sum of losses over the entire data set, which is this. So this is the output by the model or the function you are trying to obtain by training. And the two label, take the negative log likelihood and sum over them, right? So if you plug the definition of f into here, then yeah, the function you are trying to minimize is exactly this. So so here's the framework that and the specific goal of the training. So but how we actually train the model or define the weights that minimize the loss over the entire data set. So yeah, again, the task is to find the parameters or weights that minimize the loss. So like I already suggested, it actually boils down to minimizing a function that takes a lot of parameters w here, and the function you want to minimize looks something like this: the summation over the entire data set, the error or the loss between the function output and the true output. So we do so by computing the derivative of this loss function L with respect to W, so the parameters we want to change, and move W to its opposite direction. So this is something called the gradient descent. So you simply modify the weights or the input to the loss function to the direction of derivative of L with respect to the weights. And well, we take the negative, so we make we move the W to the opposite direction of the gradient. So this eta is a small value which controls the learning rate, how much you wanna move the W at a time. So we simply repeat this until L converges or no longer decreases. So why this gradient descent method at least mathematically works? So this is a simple fact about the gradient or the derivative. So if you move W or the whatever input to the function slightly by delta W, then the value of this function uh, will increase approximately by this value, the gradient of the function multiplied by whatever value you change the input, right? So this is the definition of gradient of a function. So if you move W slightly to the direction or the more precisely the opposite direction of the gradient, and that is to say delta W is something like this, then you simply plug this value of delta W here, and then you get something like this. So if you plug this value to here, so here you are taking the essentially the inner product of two same vectors, right? So this part is always positive. So the right hand side is always smaller than the left hand side. I'm sorry. I'm sorry. So the right hand side is always slightly smaller than this value alone. So in other words, L will decrease by moving W to this direction. So this looks somewhat abstract. So let me show you how it actually works in a specific simple example, just to give you a sense of sense that it is something you can do by simple programs or the computer programs. So let's get back to the linear regression example which I have given earlier. So in this specific linear regression example, the loss function looked something like this, right? So you want to find the parameters over three real values W0, W1, and W2 that minimize this value. So you simply differentiate this expression by W or each of W0, W1, and W2. And you get this one. So it is a simple high school mathematics. So simply the differentiate this expression by, let's say, W0, then you get because this is a composite function, so you apply something called a chain rule. So some complex functions at the square of some complex function, you differentiate it by W0. So you first get 2 of whatever is this complex function right here, right? Then you simply differentiate this complex function, whatever is inside this parent, by W0, and you get obviously 1, right? So similarly, if you differentiate this one by W1, then so this part is exactly the same. But if you differentiate what's inside this parents, you get Wi instead, right? And if you differentiate it by W2, you get xi square here, right? So this is something you can very easily do by computers or even on papers. So the gradient descent method simply repeats this. So updating W by um, this value until L no longer decreases. So this is how you can actually do this linear regression. So there's one practical problem with the very simple gradient descent method I have just described. So this is that okay. So the loss function we want to minimize. It is normally a summation over all training data. So you take the sum over the entire data set. So the gradient descent method I have just described compute this error function. The derivative or the gradient of this error function with respect to W for each training data with the current value of W, and then sum all of them over the whole data set, right? So you are taking the sum of the whole data set, and then update W by the expression I have just shown in the last slide. So the problem I'm talking about here is the D may be huge, right? So the taking the sum over the whole data set or the um, computing the derivative of error function for all the data in the data set is taking time, right? This is the problem. Yeah, you may think that you will be doing it anyways at one point, but the true problem is that so you update W only after computing the derivative or for the all the data set, and then update W only once. So this is in a way very um, sort of costly, considering the purpose is to reach the good value of weights as soon as possible, right? So it is very commonly observed that the convergence that becomes much faster when we update W more incrementally or more frequently. So which leads to something called the stochastic gradient descent, or simply called SGD. So here's what SGD is. So the only difference between SGD is and the original gradient descent I have just described is that SGD works on a subset of the training data set at a time. So it repeats, so randomly drawing a subset of training data, let's call it the D prime, and it is also commonly called a mini batch, which is a subset of the entire data set, and compute the gradient of loss over the mini batch instead of the entire data set as it was in the gradient descent. So mathematically, the only difference is that you take the sum over the D prime instead of the entire data set D. And you update a W in exactly the same way as before. The only difference being that the loss is obviously computed only with respect to the subset of the data set, which is a mini batch. So in other words, the entire workflow looks almost exactly the same, except that um, So you take the subset of the data set at a time. So in other words, so the other way to look at this is, so you update a W more often than before. So in the original gradient descent, you update only after you process the whole data set. But in this case, you take a small subset of the entire data set at a time. So you update W with only only the loss value computed with respect to the mini batch. So either case, so what is left for you to understand to finish the implementation of a neural network is how you actually carry out this taking derivative of a specific loss function. Because you some in some way you fix the expression of f parameterized by w, and you also well choose whatever loss function you think is appropriate. So in our case, it was negative log likelihood function. So taking the derivative of this expression with respect to w is mathematically, well, obviously a doable thing. But how you actually carry out in computer programs is slightly another thing. So this is what the remaining part is actually all about. So computing the gradients. So the challenge here is that the function you are trying to build is a complex function. So in neural networks, a function is typically a composition of many stages or something called layers. So each represented by possibly a lot of parameters. So this is the sort of a template of neural networks. So in the first stage or the first layer, well, you do something. So using some known function, a convolution or matrix vector multiplication, or well, so what I said as a ReLU or MaxPool or softmax or whatever. So you introduce a known fixed function parameterized by W1, and you apply this function to the original input to get some another value. Let's call it x1, and you use this value to compute another value x2 by applying another possibly parameterized function f2. So you repeat this until you get the output of the uh, entire neural network or the model. And then you compute the error between whatever is output by the model and the true output. So you to get the loss. So the mathematically speaking, you have to be able to differentiate this loss L by each of W1, W2 through Wn. So this is what you have to be able to do mathematically, why to implement neural network. So another factor that makes it somewhat more challenging. So it is not necessarily a very challenging mathematically if you get the basic mathematics right, but still something that makes the whole thing more complicated is the fact that each of these x, x2, x1, x2 are all not a single real value, but many values, so vectors or two-dimensional arrays or these things. And so as such, the relation between what you have in the next layer, xi plus 1, and whatever you have in the previous layer xi, why it can be as complex as this. So you have to be able to differentiate in the setting that all these variables may be vectors, or well, in terms of the implementation, multi-dimensional arrays, two-dimensional arrays. So, but the okay, so in the specific example of the digit recognition, well, it can be expressed in something like this, and you have to be able to differentiate this L by W0 and W1 here. So here's what SGD is. So the only difference between SGD is and the original gradient descent I have just described is that SGD works on a subset of the training data set at a time. So it repeats, so randomly drawing a subset of training data, let's call it D prime, and it is also commonly called a mini batch, which is a subset of the entire data set, and compute the gradient of loss over the mini batch instead of the entire data set as it was in the gradient descent. So mathematically, the only difference is that you take the sum over the D prime instead of the entire data set D. And you update a W in exactly the same way as before. The only difference being that well, the loss is obviously computed only with respect to the subset of the data set, which is a mini batch. So in other words, the entire workflow looks almost exactly the same, except that um, so you take the subset of the data set at a time. So in other words, so the other way to look at this is, so you update a W more often than before. So in the original gradient descent, you update only after you process the whole data set. But in this case, you take a small subset of the entire data set at a time. So you update W with only only the loss value computed with respect to the mini batch. So either case, so what is left for you to understand to finish the implementation of a neural network is how you actually carry out this taking derivative of a specific loss function. Because you in some way you fix the expression of f parameterized by w, and you also well choose whatever loss function you think is appropriate. So in our case, it was negative log likelihood function. So taking the derivative of this expression with respect to w is mathematically, well, obviously a doable thing. But how you actually carry out in computer programs is slightly another thing. So this is what the remaining part is actually all about. So computing the gradients. So the challenge here is that the function you are trying to build is a complex function. So in neural networks, a function is typically a composition of many stages or something called layers. So each represented by possibly a lot of parameters. So this is the sort of a template of neural networks. So in the first stage or the first layer, well, you do something. So using some known function, a convolution or matrix vector multiplication or well, so what I said as a ReLU or MaxPool or softmax or whatever. So you introduce a known fixed function parameterized by W1, and you apply this function to the original input to get some another value. Let's call it x1, and you use this value to compute another value x2 by applying another possibly parameterized function f2. So you repeat this until you get the output of the uh, entire neural network or the model. And then you compute the error between whatever is output by the model and the true output. So you to get the loss. So the mathematically speaking, you have to be able to differentiate this loss L by each of W1, W2 through Wn. So this is what you have to be able to do mathematically, why to implement neural network. So another factor that makes it somewhat more challenging. So it is not necessarily a very challenging mathematically if you get the basic mathematics right, but still something that makes the whole thing more complicated. It is the fact that each of these x2, x1, x2 are all not a single real value, but many values, so vectors or two-dimensional arrays or these things. And so as such, the relation between what you have in the next layer, xi plus 1, and whatever you have in the previous layer xi, why it can be as complex as this. So you have to be able to differentiate in the setting that all these variables may be vectors or well, in terms of the implementation, multi-dimensional arrays, two-dimensional arrays. So, but the okay, so in the specific example of the digit recognition, well, it can be expressed in something like this, and you have to be able to differentiate this L by W0 and W1 here. So this is what a chain rule is exactly for. So, but before getting into the chain rule, so see here the review of what the derivative of multivariable functions or the functions taking multiple variables. So how you differentiate multivariable functions. So let's say the input to the function x is n element column vector. So f of x is a scalar. So in the case of a neural network, f is going to be the loss function. So here's the definition of the gradient of f with respect to x, which is a vector, which is still written in the df over dx. It is a row n vector, so n element row vector that satisfies the following approximation, which is that the changes to f, if you slightly change the input x by delta x, can be approximated by the product of two vectors. So this is row vector, and this is a column vector. So by multiplying these two, um, you get a single real value, scalar value. So it's essentially the inner product of two vectors. So in terms of the component, you can write the same thing as like this. And so it is known that when such a vector exists at all, well, it is simply this. So the ith component of this vector is simply the partial derivative of f with respect to the ith input variable xi. So the in terms of the vector, it is simply the list of partial derivatives for each of input variables. So in other words, this delta f changes to f can be approximated by this summation. So this is another way of defining the derivative of f with respect to this multiple input variables. So here comes the chain rule. So we consider a function f that depends on y. Let's say it is a m element vector, but each of which in turn depends on another input x. So which is n element vector. So the situation can be illustrated like this. So in a way the original input, or let's call it the downstream variable, is x, which affects the value of y, and we are taking the the function of y. So this is exactly the situation we have in the neural network, right? So eventually we want to compute the loss, um, which is a single value, but we like to the take the gradient of f with respect to variables in the lower part of the network, right? But anyway, let's get back to the pure mathematics. So the all virtually all mathematical textbooks tells this chain rule. So chain rule says that so the gradient of f with respect to a variable xi here can be computed by the sum of these terms. So each term is the gradient of f with respect to an element of y here, yj, multiplied by that y variable, the gradient of that y variable with respect to the input variable xi. So you sum up all these terms over the older y variables. So this is the intuition behind this seemingly complex chain rule. So let me get back to the definition of the gradient for a second. So just look at this. So let's say we want to obtain this derivative of f with respect to variable xi. So what we like to get is, so let's imagine that you slightly increase xi by delta x, delta xi, then well, how much amplified this change is to the output of f. So considering the all other variables do not change, so you change only the particular xi by delta xi. So then, how much changes will happen to f? Well, more specifically, how much the changes to the xi is amplified. So this amplification factor is exactly what we want to get, the gradient of f with respect to xi. Let's imagine that so you slightly increase this particular variable xi by delta xi. So then, well, actually, the changes to f happens in many ways. So because xi might be affecting each of these y, right? So, but let's consider for a second. So how much change happens to this particular variable yj? So it is exactly this, right? So according to the definition of the gradient. So the gradient of yj with respect to xi multiplied by delta xi. So this is exactly the change that happens on the particular variable yj, right? And because yj increases by this much, the changes that happen through the increase of this particular variable yj can be written like this, right? This part is exactly this part. So how much change happened on this particular variable yj, and because yj will be increased by this much, then f will increase by this much. So in other words, the change to f will be amplified by another factor of uh, df over dyj, right? So this is the a change to f that happened through this particular variable yj. So because by increasing xi slightly, well, actually each of these yj's might change, right? In total we have a change to f that can be described by something like this, which is the summation over all y variables. So for each variable, f will be increased by this much. So this is the intuition behind apparently very complex formula. So this chain rule is actually all you need to carry out the actual computation of the gradient. But this mathematical formula is actually not necessarily very convenient to use in the actual computation. Because, okay, so if you get back to this, the exact formula, uh, it is using the index variable I for x and j for y, but in the actual code, I and j may be used for some other purposes, and there may be even cases in which you have multiple indexes for x and multiple indexes for y. So if you just remember exactly this formula, well, it's still very confusing when you apply this formula in the actual code that uses multiple array dimension, multiple dimensional, multi-dimensional arrays everywhere. So, I recommend you to master this chain rule, which I call the machine learning practitioners version. So we don't use indexes at all, just to express what the chain rule says without using indexes at all. So the situation is, yeah, again, like this. So you have y, for which we can compute f, and x that affects y, and we like to get the derivative of f with particular x here. So to obtain that, you simply remember the chain rule in this form. So you sum over all variables y that this particular x directly affects. So in general it may be all of them, but well, in some cases it may be only a part of y. But anyway, so you sum up over all variables that this particular x may affect, or directly affect this term. So df over dy multiplied by dy over dx. So this is actually very convenient to use. And so both x and y are just as a single scalars in this case. So no indexes you have to remember. Just remember this one and translate this into the actual code. Well, this can be done no matter what kind of arrays x and y actually are. So this is the chain rule, and here's why this helps you implement a neural network. So this is what a simple neural network actually looks like, and this is the loss function you wanna minimize, and it is computed by the from the original input x as well as these weights, and you wanna obtain the gradient of L with respect to these weights, well, just to update these weights in the right direction. So chain rule allows you to compute the derivative of loss with respect to a variable in a layer if you are already given the the derivative of L with respect to another variable y that is above x in the network layer. So let me say this more specifically. So for example, this is the function you wanna take the derivative of, but it is simple to get the derivative of L with respect to y that is directly below L in the network, right? So because it's simply the result of applying a single function, a negative log likelihood. So if you simply apply the derivative, so the mathematical formula of derivative of log, you can easily get the derivative of L with respect to y. So now you have the derivative of L with respect to y. Then by applying the chain rule, you should be able to get the derivative of L with respect to this variable, that one step below y in the network. Well, you simply repeat this. So you get the derivative of L with respect to this x4. Then, but chain rule allows you to obtain the derivative of L with respect to x3. By the way, so if you have the derivative of L with respect to x x4, then you should be able to get the derivative of uh, L with respect to this W1, which is the part of what you exactly want. But you repeat this along the network until you get derivative of L with respect to this x1, and then you get the derivative of L with respect to this W0. So you repeat applying chain rules to obtain the gradient of L with respect to a variable in all the layers of the network. So this is essentially all you need to know in terms of the framework that enables deep neural network. And this entire thing is commonly called the back propagation because the gradients are computed the backwards, right? So in the opposite direction along which you compute the actual output of the network. So what remains is so how you compute the derivative between two adjacent layers. For example, um, so so let, let's say you are given the gradient with respect to this variable. How you get um, the gradient the gradient with respect to this variable, which amounts to obtaining the dy over dx for each variable y here and for each variable x here. So this is purely about applying some appropriate mathematics formulas for each layer. But the only complication or the challenge is the fact that all variables are actually multi-dimensional arrays and with so many indexes. So you are very confused which index is used for what and how you actually apply the mathematics formula into the particular representation of each input and output. So in this section, we go through many component functions used in the neural network we have. So here the functions used in the neural network we are using. So convolution, linear, ReLU, and other things. So in this section, we are going to summarize their definitions, not necessarily all. So I just missed the omitted the definition and derivatives of max pool and dropout. Hopefully that hoping that it is very simple to do, given you learned you learned some other things. So this is the convolution. So let me get started with the convolution. So the convolution takes an image, which is, or in the case of 2D images, 2D pixels multiplied by a number of channels. So a channel means a component in image. So for example, in the grayscale or black and white image, the number of channels is actually the number of channels is actually one. But in the color images, it may have three channels, so R component, G component, and B component, for example. And another thing that it takes is a filter or kernel. So which is essentially another small image like this. So it is given a filter and an image. It computes the output like this by the following. So it slices the filter, the small image over all pixels of the input, like this, and takes the inner product at each pixel. So the inner product between the kernel and the pixels in the input image. For example, in this particular point, it essentially takes the inner product of two 9-element vectors, 3 by 3 pixels, between the filter and corresponding pixel values of the input. And the computed inner product is put in the corresponding position in the output. So in this particular case, so because the filter is 3 by 3, well, actually, well, just to avoid overflowing some of the element outside the input image, the 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 the, uh, the output images are slightly shrinked, so shrinked by 2 pixels on each side. Well, there's other version that somehow maintain the size of the original image, but the particular implementation we are using shrinks the image by 2 on each side. So this is the illustration assuming there's only a single channel. So this is what 2D convolution actually looks like. So in terms of the mathematical formula, the filter is essentially a k by k 2D array. And well, actually, the actual implementation of a convolution layer takes another something called a weight, so something like a weight called the bias, which is simply added to each output pixel. And input images are, let's say, H by W 2D array, Xij, and Y, so the output image Yij, well, is, like I said, it is slightly shrinked by 2 pixels on each side. And the exact expression is like this. So the output pixel at ij position is essentially the inner product between W and the corresponding pixels of the input image, like this. And but in addition to this convolution, the convolution layer was adds something called a bias to each output pixel. So this is the single channel version, and the actual implementation of both input images and output images have multiple channels. So let's say the input image has AC number of channels, and the output images have OC number of channels. So in that case, a filter is defined between each of the input channel and the output channel. So now the filter is a 4-dimensional array. Bias is defined on each output channel. So the bias is now a 1-dimensional array. An input image is a 3-dimensional array, obviously, because it has a number of channels. And similarly, an output image is a 3-dimensional array. So this is the mathematical formula for convolution for a single input image that may have multiple channels. So yeah, in a way, it's essentially doing the same thing, but the inner product is taken for somewhat a larger vector, because it is now um, taking the sum over all the input channels. And what's more, in the actual code, uh, where it does this operation for all the samples in a mini batch. So it introduces another variable s that denotes a particular sample in a mini batch. So what the code is doing is actually like this. So for all the input pixels of all the output channels of all the sample, you do this. So the main thing now is how you um, how you do the back propagation. So they call that the back propagation is essentially about obtaining the gradient of the loss with respect to the input to the layer. Given that you already obtained the gradient of the loss with respect to the output y of the layer. And x and y, so input and output is connected by using this formula. So this is simply applying the chain rule as I described in earlier slide. So you wanna get the derivative of L with respect to each of the input x variables, and what they call that the chain rule uh, takes the sum of all the input all the variables of y. So because y is indexed by these four indexes, we are taking the sum over all the uh, four indexes, right? And yeah, this is the y variable corresponding to a particular index here. So this is purely applying the chain rule, and you simply compute this part by looking at looking at this connection between x and y. Well, basically you simply well, so look at the details by yourself. But well, basically what happens is that you uh, take the gradient of this term with respect to this variable, and you get something like this here. So this term is replaced by one of those weights. So work out on the details by yourselves. I don't want to go back and forth between two slides and explaining whether the index is exactly right. So you do similar thing for obtaining the gradient with respect to W, which is you actually the part of the goal for applying backpropagation. And you also need to get the derivative with respect to bias. So just to confirm that I'm doing this right. And yeah, when you look at the code later, well, just confirm that the code is exactly doing what is written here. So this is the linear, or also known as the free connected layer, whose definition is simply you multiply x by another matrix W and plus bias. So the definition is as simple as this. And you do the back propagation and just doing exactly the similar thing as before when we did it for convolution. So because y is indexed by I, applying the chain rule, we take the sum over all the indexes for y, and each term looks like this, dl over dy multiplied by dy over dx. And just by looking at this, I'm sorry, what I'm doing. So sorry. So looking at this definition, so you derive this term, and essentially what happens is that so you take the gradient, you get the gradient of this term with respect to this variable and get yeah, something like wij. So this is what happens here. So you do the similar things for w and b, and you get this. So this is another layer called ReLU, or rectified linear unit. Well, it's actually a very simple function. So the definition of ReLU for a real value, a scalar value, is simply the maximum between x and 0. So if x is positive, then y is simply x. And if x is negative, then y is 0. So derivative of ReLU is, well, not surprisingly, very simple. So dy over dx is 1 if x is positive, and 0 otherwise. Also, you can simply write it as max sine x 0. So sine x is 1 or minus 1 between, and depending on x is positive or negative. So this is a one real value version of ReLU. And in the neural network, we simply apply this ReLU on each component of a vector. So this is the vector version of ReLU. So I write these capital letters just to signify that this is applied for a vector. So it is simply the application of small ReLU to each component like this. Therefore, the derivative of ReLU is simply dy over dx is max sine xi 0 if both variables are have the same index, and otherwise 0. So this is how you do the back propagation through the ReLU. So again, so y is indexed by I, right? And derivative of L with respect to xj is like this, just applying the chain rule. If you take the sum over all the i's, well, all the components except I equal j is simply simply zeros. So the only one term remains, and this is simply it. So if xj is larger than 0, then well, only this term remains, because this is 1 and otherwise 0. So the rule is very simple. So I'm going to omit the description of max pooling and dropout. So you can take a look at the code, or you can simply Google them. So let me get into the final part of the network. So it is very typical to have this layer called softmax at the last layer of the neural network for classification problems. So the definition looks like this. So you basically take the exponential of each component. Um, you simply normalize the this exponential by dividing it by sum of all these components. This is essentially a normalization term that guarantees that the sum of all these components become exactly one. So the softmax is a vector whose each component is always larger than zero, or maybe well, it's larger than zero. It's always positive. And some of all components are guaranteed to be one, just by the normalization that is happening here. And the more importantly, this had the effect of, well, amplifying the largest component. So this is what typically happens. So the input is looks something like this. There may be positive ones and negative ones, and this one is the largest one. Because we are taking the exponential of each of them, this one gets much larger than other components, right? So the output softmax looks more like this, and the largest one becomes closer to one, while other ones sort of diminish. This is the effect of softmax. So by doing this, we are trying to sort of interpret the result of softmax to be the probability that a particular input belongs to each class. So what we typically do in the neural network is, so the right before the softmax layer, we have something called the scores, where the score may be an arbitrary value, both positive or negative, but still maintains that if the likelihood that a particular sample belongs to a particular class is larger, then the score will be larger. So this is what the earlier part of the neural network tries to accomplish. The softmax converts this score into something that can be interpretable as the probability, right? So this is what the softmax is basically for. And in our typical classification network, including ours, this softmax layer next goes through the loss function called a negative log likelihood. So the first thing that happens right after taking the softmax is applying the log function on each component. So just recalling that the softmax looks like this. So just take the log of each component, that you get something like this. So this one comes from taking the log of this. So the canceling log and exponential. And this term obviously comes from the logarithm of this factor. So the actual loss function we are using is something called a negative log likelihood, whose definition is given here. So the loss between x and t is defined by this. So t is the true class of the data, and x is an element vector whose each component of which is supposed to represent the probability that particular sample belongs to each class. So the loss actual loss function is simply like this. You simply take the component of x corresponding to the true class and take the negative log. So that's why it is called the negative log likelihood. So therefore, so all combined, so the sum values going through softmax and then going through negative log likelihood, uh, you get something like this, which is simply the negative of what we have just computed. So the negative of the t's component of this vector, so which is exactly this. So here's how you apply the backpropagation for the layer combining softmax and NLL. So we don't do it individually. So we just treat the two layers as if it is a single layer because it's convenient. So in this case, so the x and y are connected like this. And again, the problem is to get the derivative of loss with respect to each of these x variable, given that you are already given dl over dy, so the derivative of l with respect to y. By the way, in this case, y is already a single real value, so you don't have to take the sum over many y variables at all. So you simply multiply dl over dy by dy over dxi, and you obtain this dy over dxi just by looking at this definition. So which is, yeah, very simple mathematics. So the only thing is that depending on I, whether I is the true label or not, um, the derivative of this term either becomes 1 or minus 1 or 0, right? So, and it can be more conveniently remembered by this. So that's basically everything you need to know to implement the neural network I gave the baseline code for by yourself, based on the mathematics if you like to. So of course you don't have to because the baseline code is already implementing what's described in the slides. But in case you are interested in being able to do it all by yourself based on the mathematics, basically, and this is what all you need to know. This is all you need to know. So in the last two slides, I'm gonna make a brief comments about the negative log likelihood layer that follows the softmax, where especially in case you feel that this is well, this doesn't sound very necessary, or this at least looks more complicated than truly necessary. So, um, so remember that for n-way classification problems, the output of the softmax layer is an n-element vector, and each component, specifically pi, it is meant to be the probability that the model thinks a particular sample belongs to that class I. So if this is the probability, this is the output from the softmax layer, our goal is to simply make a PT, the probability that the model thinks the particular element belongs to the true class T. The T is the true class. So, close to 1. So the goal is simply to make PT close to 1, right? So for that purpose, you might be wondering, a loss function could be any function that decreases with PT. or something as simple as negative PT. So you don't have to take the log. So for what is the point of this log in particular, right? So even if the loss function is as simple as this, if you want to minimize it, you want to make PT larger, right? Or I should say, so if you try to minimize negative PT, you are effectively maximizing a PT, whether very probability that a particular sample belongs to the true class. So which is exactly the goal. So again, so you might be wondering what is the point of taking the log here? So this is because, well, actually the goal is to maximize the joint probability of the entire data, which is the product of probabilities of individual samples. So the true goal is to maximize this value, the product over the entire data set, PTK. So TK is the true label of sample K, right? So the goal is to make the model that maximizes this value, right? And the other thing you have to be noted is that the loss over min batch, or the entire data set for the matter, is the sum, not the product of losses of individual samples. This is precisely how we define the losses over the data set, whether it's mini batch or the entire data set. So actually, the effect of taking the log is to reconcile the slight difference between the sum and product. So they can be reconciled by setting the loss function to uh, negative log PT. Because so if you sum negative log PT over the entire data set, you are actually taking the negative log of product of all these terms, right? So therefore, so if we are able to minimize this left-hand side, well, you are in effect minimizing the right-hand side, which is equivalent to maximizing whatever is inside the parent, which is the product of um, all the individual sample probabilities. So this is precisely the reason why we like to define loss function like this.